A lone roller. A lone roller in the form of a thin-walled hollow cylinder with mass capital M is pulled horizontally with a constant horizontal force F applied by a handle attached to the axle. If it rolls without slipping, find the acceleration and the friction force. Okay, so first of all, hollow cylinder, what is the moment of inertia? The hollow cylinder has an inner radius R2 or R1, outer radius R2. If this is going to be a thin-walled cylinder, for the case of a thin-walled hollow cylinder, we will have these two radii equal. R2 and R1 is equal to capital R, so you can see that the moment of inertia becomes r squared plus r squared over 2, so it's mr squared. Now, this is our lone roller. Here we're applying a constant horizontal force F through a handle that's attached to the axle, about which we're rotating. There's the weight of the cylinder, there's the normal force from the surface, and because it's going to have an angular acceleration in this direction, we need a torque that will be causing this rotation in the clockwise sense, and that torque will be provided by the static friction. So it's R cross F basically will give us this sense of rotation. Now, if we write Fs, the static friction, it must point in the coordinate system that I have developed here in a minus I hat direction, and how did I find the direction of the static friction? I need an agent that can provide the necessary torque. So this is the force that's providing the necessary torque for rolling without slipping. Now, if I write Newton's laws of motion, the net force on the x-axis is basically the external force F, horizontal force F being applied, minus the static friction force, that's equal to the mass of the cylinder times the acceleration of the center of mass, the translational motion. The net torque provided by the static friction, if you use the right-hand rule, point from the axle towards the application force of the static friction with 4 fingers, curl them towards the static friction, you see that the torque will point in minus k hat direction. So this is minus r fs k hat, which is equal to I alpha, Newton's second law, rotational form. And this is a central axis. So the angular acceleration alpha we will find minus r fs over mr squared k hat. So it's the angular acceleration is in minus k hat direction. The r's will cancel here, so we will get rid of one of the r's, and we will be left with a minus static friction force divided by mr k hat for the angular acceleration. In rolling without slipping, the acceleration of the center of mass is linked to the angular acceleration as alpha times r, and alpha, the magnitude of angular acceleration, is fs over mr, so fs over mr times r, which is static friction fs divided by m. So if we go to the x component of the forces, Newton's second law applied to the translational motion, we see that F minus Fs is equal to mass times center of mass acceleration, which is Fs over m. So these m's will cancel, and we will obtain F is equal to 2Fs, or the static friction force is equal to capital F divided by 2. So it's the force we're applying divided by 2. That's the static friction. Acceleration of the center of mass is basically Fs divided by m. So that would be equal to F divided by 2m. Okay, so we have a lone roller. It's a 10-volt hollow cylinder. We can figure out for a cylinder that has inner and outer radii R1 and R2. In the 10-volt case, these two radii become R. The moment of inertia is mr squared for rotations about the center. It's pulled with a constant horizontal force using a handle attached to the axle. So this force has no torque effect. The weight and the normal force have no torque effects. However, the static friction will have this torque effect here. So we need the static friction to point in minus I hat direction. If we write Newton's second law, for the x component of the forces, F minus Fs must be equal to mass times center of mass acceleration, and the only force responsible for the torque is Fs, which is minus Rfs k hat. It is equal to I alpha, Newton's second law rotational form. From this we can determine alpha is equal to minus Fs over mr k hat, when we substitute mr squared for moment of inertia. And center of mass acceleration is alpha times r, it's Fs over m. So going back to this equation for the x component of the forces, F minus Fs is equal to mass times center of mass acceleration, Fs over m. So we find that Fs is F over 2, and center of mass acceleration, which is Fs over m, is F divided by 2m.